Hi students, today we will discuss about the lecture 4 of atomic structure module 1. So today we will discuss about the Aufbau principle, the Hund's rule, and also you can know about the Pauli's exclusion principle, and also we will check the electronic configurations of some of the elements. So let's start. So students, today we will discuss about the lecture 4 of atomic structure. That is our last lecture of the atomic structure, and this is module number 1. Okay, now you can hear me well. So this is the subject name, that is chemistry. The code is CH101 or 201. Credit is 3 and lecture hour is 34. And these are the course objective. Now these are the some of the course outcomes. Here I have given the lecture plan. So our today's lecture is lecture 4. That is the last lecture of the atomic structure. Today we will finish the chapter. Okay, so these are the some of the objectives of the class. That is today we will discuss about the atomic orbital. You can know what are the atomic orbitals we have, actually why we have these atomic orbitals, that all the things you will know. Next, we will discuss about the Pauli's exclusion principle, Hund's rule, Aufbau principle, and some of the electronic configuration of some elements that we will check. Because in your exam, there are from this portion, you may have this type of question. You are given some of the elements, the list of the elements, and for each and every element you have to find out the electronic configuration. You have to write down the electronic configuration. Actually, it's very easy. If you know how to write the electronic configuration of each element, you can write very easily. Okay, one thing you should know about the atomic number. Okay, and the last one is the Schrodinger equation. Actually, Schrodinger equation only you have very brief, very little amount that you have in your syllabus about the Schrodinger equation. So all these topics we will discuss today. Okay, so these are the some of the recapitulation. In the previous class, we have discussed about the Sommerfeld model. According to the Sommerfeld model, what? The electrons are revolving around the nucleus in a elliptical orbit. For that, for each and every principal quantum numbers, we have some of the sub-levels of the energies. Okay, like s orbital, p orbital, d orbital, f orbital. These are the orbitals coming from the Sommerfeld atomic model, and this is an he has incorporated one more quantum number, that is the azimuthal quantum number or orbital quantum number. This is Zeeman effect. Now next we have discussed about the Zeeman effect. Zeeman effect, generally if we apply the magnetic field, then what will happen? What will be the orientation of the electron? What will be the orientation of the energy levels? What will be the shapes of the energy levels? All these things we can know from the Zeeman effect. Okay, and if we consider the magnetic effect, so that time also we have to incorporate one more quantum number, that is magnetic quantum number. And at last we have introduced introduced to the 4 quantum numbers. These quantum numbers actually are very important, very important for one electron, for an electron, which is the actually address of the electron, you can say. If we know the 4 quantum numbers, you can say the electron is in s orbital, the electron is in this principal quantum number, and or you can say the electron is in px, py, pz, or dx square, y square, whatever the accommodation of the electron, that you can know from the quantum numbers. Okay, now this is a quick review. Whatever I have discussed in previous class, how much you have got. So that's why, for checking that, so I have given one question. By which quantum number we can know the orientation of the orbital within the subshell? Okay, this is a question, and for this you have 10 seconds. Your time starts now. You have to just memorize whatever I have taught in previous class. Then only you can get the answer. Yeah, your 10-second time is over, and you are absolutely right. Yes, it is the magnetic quantum number. From the magnetic quantum number, we can know the orientation of the orbitals. Okay, so from this quantum number, like d orbital, what are the if we apply the magnetic field, so what will be the orientation of d orbital? There are 5 degenerate energy levels that we are getting. That means 5 5 levels, 5 orientation of the orbitals we are getting. In presence of magnetic field, the p orbital is having 3 orientation. Okay, f orbital is having 7 orientation. So all this we can know from the magnetic quantum number. Okay, so these are the quantum numbers. Generally, we have 4 quantum numbers. The principal quantum number, which we have got from the Bohr's atomic model, that is n. N can be 1, 2, 3, 4, any numbers. Okay, so this is called principal quantum number. Next, we have azimuthal quantum number or angular quantum number. If we consider that the electrons are revolving around the nucleus through the elliptical orbit, that time we can get this type of quantum number, that is azimuthal quantum number, that is denoted by L. If L value is 0, it will be S. If L value is 1, that is P. If it is 2, it indicates d orbital. If it is 3, it indicates f orbital, and so on. Okay. Okay, generally the L value will be 0 to n minus 1. If n value is, look here, I have given L is, the 0 means s orbital, this is p orbital, this is d orbital, and L equals to 3 means f orbital. Okay, so L value will be 0 to n minus 1, any values it can have. Next is the magnetic quantum number. That means if we apply the magnetic field, the energy levels will be oriented in some other levels. The orientation will be different. So based on that concept, again we have to introduce one quantum number, that is magnetic quantum number, and which is denoted by ml. Okay, and this ml value should be minus L to 0 to plus L. If L value is 2, So the ml value, the magnetic quantum number will be -2, -1, 0, +1, +2, like this. Okay, so that is why d orbital is having 5 orientation in presence of magnetic field. Okay, and total of, this is the expression, that is total of 2l plus 1 orbitals in each subshell that we will get if we do the 2l plus 1. Excuse me. So here s orbital, if it is s orbital, that means L equals to L value is 0. So ml value is also 0. If it is p orbital, for p orbital L value is 1. That means ml value would be -1, 0 and +1. So three orbitals orientations we are getting, px, py and pz. For 5 d orbitals, 5 degenerate levels we are getting, that is dxy, dy, yz, dxz, dx square minus y square and dz square. These are the 5 levels orientations that we will get. Same as for the f orbital also, we are getting the 7 levels, 7 orientations. Okay, so this magnetic quantum number is totally dependent on the azimuthal quantum number. Okay, next is spin quantum number. Spin quantum number means if in an energy level 2 electrons are there, maximum 2 electrons will be there in an orbital. So what will happen in an energy level? So what will happen, the one electron, if one electron will be clockwise addition, then other electron will be anti-clockwise addition. Okay, so this is called spin quantum number, and which is denoted by ms. The value of the ms will be plus up or minus up. Okay, and sometimes it will also called by the up and down. Okay, so these are the some of the quantum numbers. What are the quantum numbers according to, if n equals to 1, what are the quantum numbers? If n equals to 2, what will be the quantum numbers? So these are the some of the quantum numbers. Okay, now we will discuss about the atomic orbitals. Now, atomic orbit, we have some of the differences between orbit and orbital. Orbit means the electron will revolve the nucleus in a specific track, that is called by orbit. And why we are calling it by orbitals? Orbitals means not the specific track. We are generally by orbitals, we are generally it means that the finding the probability of the zone where we can have the probability of finding the electrons. Okay, so these are the some of the s orbitals. S orbitals are generally sphere. Okay, so and this you can see the blue zone, that is finding the probability of finding electron, a zone. So this is called orbital. Now what does it mean, node? Node means actually means that there we don't have, very less amount of probability of finding electrons are very less, so that are called nodes. Okay, the atomic orbital is defined as three-dimensional space in the atom where probability of finding electron is maximum, as I told you. The equation to determine the number of orbitals in a subshell is 2l plus 1. Already you know that. The shape of the these are the some of the shapes are given, that is s orbital spherical, p orbital is dumbbell shape, d orbitals, you know, d orbitals very complex, f orbitals are also very complex. Okay, so first energy level has first sub level, that is s. Second energy level has two sub levels, as that is s and p exactly. third energy level has 3 sub-levels S, P and D, and fourth energy levels of 4 sub-levels that is called by S, P, D and F orbitals. Orbitals, that means what? Orbitals are not specific track. It doesn't have any boundary, only a zone, a space where we can find the electrons. The probability of finding electrons in that space, in that area, will be high. That is called by orbitals. Okay, so you know already these are the three p orbitals. One is pxy, pyz, px, py and pz. Three types of orbitals we have for the p orbital, and d, for d orbital we have 5. d, yz, dxz, dz square, y square, and dx square minus y square, and also d xy. Okay, so these are the 5 types of orbitals we have. Next, this is the F orbital. Generally, we have the 7F orbital. Okay, so there you can see these are the dumbbell shape. These are the lobes. You can see that is the probability of finding electrons. Okay, the zone of the finding electrons. Okay, next we will discuss about the Aufbau principle and its limitation. Aufbau principle generally, according to, if we know the Aufbau principle, then we can accommodate the electrons in the energy levels. According to this principle, the energy first will accommodate the lowest energy level, then gradually it will fill up the highest energy levels. Okay, the order in which the orbitals are filled, that is 1s, 2s, 2p, 3s, you can see here. The Aufbau is a German word meaning building up or construction. That means what? If you know the Aufbau principle, you can accommodate the electrons in the energy levels. You can know how many electrons will go in different energy levels. Okay. The Aufbau principle dictates the manner in which the electrons are filled in the atomic orbital. According to the Aufbau principle, the electron, as I told, look, first occupy those orbital which is the lowest energy level. So first lowest energy level, then gradually it will build up. Okay. With lower energy level happen completely filled. The order in which the energy of orbital increases can be determined with the help of the n+1 rule. Okay. Okay, now next, these are the some of the energy levels you know already. 1s, 2s, we have 2p, 3s, 3p, 4s for 3d, then 4p we have 5s, 4d, 5p, 6s and 4f. These are the some of the energy levels. Okay. So, according to him, the lowest energy level, that means 1 is first, we have to fill up this level. 1 is, then 2s, okay, then 2p, then 3s. Like this way, we have to go towards the higher energy level. Okay. So this is called the this is called Aufbau principle. Now some of the exception we have for the Aufbau principle, like chromium, for the chromium atom. Okay, so the electronic configuration should be argon bracket, argon in bracket, you have to write down argon, and then 3d4 4s2. This is the total number of the electrons for chromium, the atomic number. Okay, so the electronic configuration should be like this: 3d4 4s2. Okay, but actually you can see that our chromium has the electronic configuration this one, argon 3d5 4s1. Why? Okay, next one more thing you can see, like for copper. Okay, copper actually this is the actual case. Okay, but we should have argon 3d9 4s2, but that is not the actual case. Actually we have 3d10 4s1. Why? Because if the orbitals are full filled or half filled, okay, so that is more stable configuration. Okay, so to gain the stable configuration, here the electron will be in D5, that is the half filled, D5s1, that is the half filled. Okay, if we put the D4s2, that will be less stable than the half filled. Here 3d10 4s1, this is the full filled. So d orbital is fulfilled. So to gain this stability, the electronic configuration is like this. Okay, so these are the some of the exception case that we have. So while you were asking to write down the electronic configuration of the elements, that time you should be very careful. Okay, if the element will be full filled or half filled, so to gain that stability, obviously the electronic configuration will be different from the actual from the theoretical value. Okay, next one is Hund's rule of maximum spin multiplicity. So according to the Hund's rule, what we have, like we have 3p orbitals. Okay, so px, py, pz orbitals. All the energies are same. So what will happen if we have the electrons? Like if we have the two electrons 2p2, okay, so 2p2 we can write down like this, one px, or we can accommodate these two electron in a px orbital, all, or we can accommodate the electrons one spin here, another spin here, or we can accommodate this one. Okay, so this cannot happen. Why? Because according to the Hund's rule, first of all, the same energy levels, if we have the electrons enough to fill up the same energy levels, so first of all, we have to fill up the same energy levels by single electron. Okay. After filling up the energy levels with the single electron, extra if we have, that time only the electron will be paired up. Understand? So this is called maximum spin multiplicity. That is 2s1. So for this case, the value of the 2s plus 1 is higher than the other cases. So that's why like pxp d 5d 5d orbitals we have. So first of all the levels will be filled by the electrons, single electrons, and then if we have the extra electron, that time only we can pair up the electrons of the d orbital. Understand? So this is called Hund's rule of maximum spin multiplicity, that is 2s, the value of the 2s plus 1 will be higher. Okay, for a given multiplicity the term will be the largest. Okay. Next is Pauli's exclusion principle. What do you mean by Pauli's exclusion principle? So according to the Pauli's exclusion principle, the no electrons, okay, no electrons can have four same quantum numbers. Okay, if the in between two electrons, if the 3 quantum numbers are same, that means the fourth one must be different. Otherwise, it will violate the atomic stability. So, this is called Pauli's exclusion principle. Like, if we have helium, for helium, this 1:2, the electronic configuration of the helium is 1:2, right? So for this 2 electron, you can see for this 2 electron, the 3 quantum numbers are same. Like principal quantum number is 1, L is 0, ml is magnetic azimuthal quantum number is 0, that is S, magnetic quantum number is 0. Okay, so and spin quantum number, whatever spin quantum number. So these 3 quantum numbers, principal quantum number, azimuthal quantum number, and magnetic quantum numbers, for both electrons is same. So you can see the fourth one, that is spin quantum number. One is plus up, this is plus up, and this is minus up. Okay, that means the spin quantum number will be different, and that time only the electron will be stable in the same energy levels. Understand? So this is called Pauli's exclusion principle. So in between 2 electrons, maximum 3 quantum numbers will be same. The fourth one must be different for the atomic stability. Okay, now you have next one is electronic configuration. Very important portion. Okay, so because there you are given so many elements, for that elements you have to find out the what is the electronic configuration of that element. So these 3 rules, the Aufbau principle, the Hund's rule, and the Pauli's exclusion principle, these 3 rules, based on these 3 rules, you can find out, you can write down the electronic configuration. Okay, so actually 1:2, 2:2, 2p6, 3:2, 3p6, 3d10, 4:2, 4p6, 4d10. Like this way and so on. Like this way, we have to fill up the electrons from the lowest energy level to higher energy level. Understand? And in a same energy level, the electron spin must be different. And the third thing is, in the same energy levels, like p orbitals, px, py, pz, d orbitals. Okay, there are 5 orbitals, same energy levels we have. So first of all, for electronic Y, we will write down the electronic configuration. First of all electrons will accommodate the energy levels, all energy levels like px, py, and pz. Okay, after that, if we have extra electron, that time only we will paired up, like px2, py2, pz2, like this. Okay, so these 3 rules you have to keep in your mind while you are writing the electronic configuration. Okay, these are the some of the electronic configuration. You have to check very well. If you know the atomic number, then you can, it's very easy to write down the electronic configuration. And these are the some of the unusual case. Unusual case why we have? Because to gain the atomic stability, like I have told you already, for copper, the predicted, this is the predicted, that should be 3d9 4s2, but actually this is 3d10 4s1. Okay, for silver, it should be 4d9 5s2, but actually it is 4d10. You can see the d orbitals are fulfilled, f orbitals are fulfilled. Okay, here the d orbitals is half filled. So to gain the stability, for fulfilling the orbitals or half filled orbitals, the electronic configuration, we have some of the exception, but unusual electronic configuration. So while you are writing down the electronic configuration of this elements you have to keep in mind. Okay. Okay, now Schrodinger equation. So Schrodinger equation, generally very little amount you have. Schrodinger equation is very difficult concept. Okay, and a full paper we have, that is quantum mechanics. There we generally read the Schrodinger equation. Schrodinger equation, while we are considering the electrons as the wave nature, electrons having the wave nature. Okay, so that time we are getting the Schrodinger equation for an electron, that is delta square psi is the wave function, plus 8 pi square m by a square into E minus V psi, that is equals to 0, where E is the total energy of that electron, V is the potential energy. Okay, delta. Why we have used here delta actually, instead of three partial differentiation, writing the partial differentiation, as you don't have the derivation of this equation, that's why I cannot show here. Only just you should know that instead of writing three partial differentiation, we have just written that is delta. Okay, mass m is the mass of the electron, h is the, as you know, that is a Planck constant, and psi is a wave function. Psi, some of the conditions are there, that is psi must be continuous, psi must be finite, must be single valued, and probability of finding the electron overall space from plus infinity to minus infinity. Okay, so this is the Schrodinger equation. From this portion you can have very simple question. Write down the Schrodinger equation like this and explain each term like this. You can have this type of question. So just you have to memorize this equation. Okay, just memorize this equation, as you don't have the derivation portion. So memorize this portion. Only if you have this type of question, only you have to write down the equation, and these are the thing you have to write down. What is m, what is a, what is h, what is psi, e, v, what does it mean? So all the terms you have to explain, you have to write down. Okay, so this is the end of the chapter. Now again we have some quick review how much you have got from this portion, from this chapter, as this is the last chapter. Question is, what is the electronic configuration of chromium? This again and again I have told already, in I have discussed already what will be the electronic configuration. So for this you will have the 10-second time. Just memorize whatever I have taught you and answer my question. Okay, so your 10-second time is over, and you are absolutely right. The chromium, that is 1:2, 2:2, 2p6, 3:2, 3p6, 4s1, 3d5. This is not like that 3d4, 4s2. Understand? So for half filling this, the atom will be very much stable. So to gain this stability, the s orbital, the electron will go here and it will make the half fill shell. Okay, so this will be the electronic configuration. This type of question generally you have very frequently in your exam. So again I am repeating the topics that we have discussed, that is atomic orbitals, Pauli's exclusion principle, Hund's rule, Aufbau principle we have discussed, the electronic configuration we have checked, and we know how to now we know how to write down the equation, how to write down the electronic configuration, and also the Schrodinger equation we have discussed. Okay, so all these topics are checked. Okay, so students, as this is the last class, so just follow my classes very well. And I have given also one assignment. Do the assignment properly and submit it within the time. So thank you, students, and see you in the next class.